Afternoon, everyone. My name is Vinai Roopchansingh, and I'm one of the scientists in the functional MR facility in mental health. This afternoon, I hope to impart a little bit of the underlying physics and math behind what we do and the images that you're generating and seeing. A couple of housekeeping things before we jump in. If you have any questions, either during, if you're here or online, feel free, please, to interrupt. I feel with material like this, it's kind of better to address any questions right there in line with material when you're waiting at the end. Secondly, throughout the slides, there are references and links. Because I've used a lot of material when I gave this course a while back, about 5 years ago, some of the links are no longer valid. I've tried to indicate those in red. If I missed any, I apologize, let me know. But most links that are no longer valid that I use material from, I still reference, but those are indicated in red. So, all right. So here's kind of a basic outline of what I'm going to cover this afternoon. I'll talk about, the source of the MR signal, kind of what's the physics and underlying processes behind the images that we're generating and looking at. So that's kind of the source of the signal, and then how that interplays with the acronym, magnetic resonance imaging and what we do. And, there'll be a good amount of just basic physics and a little bit of math as we go through that. Then we'll talk about how that interacts with the contrast that you're seeing in the images, i.e. the difference, like why does gray matter look a little bit different than white matter? And then at the end, we'll just talk a little bit about the points that some things to consider when you want to do your experiments. And these are maybe a little bit orthogonal to what Dan Henworker talked about last week, but there's a lot of things to think about when you're doing experiments like this, and it's complicated as these. So let's just jump in, and we'll start with magnets because it's kind of at the source of what we do. So besides the big magnets, both in terms of size and in terms of field strength, the center of the MR systems that we use. At the other spectrum, we're really depending on the magnetic properties of the atoms and the nuclei of the species that we're imaging. So some nuclei here, so you see the list here, it's carbon-13, sodium, phosphorus, xenon. These nuclei have specific properties where they're, like tiny magnets, or what in the parlance they say they have some magnetic moment. But can anybody guess, besides these, what is the species or atom or nuclei that we're most interested in for MR and that we use most day to day? Anybody online? And that is absolutely correct. So someone online did mention hydrogen or protons. And that's important because, these make up water, and that is pretty much in every single part of us, except maybe our lungs. But the hydrogen atom or the proton nucleus, the hydrogen nucleus or the proton is what we use to generate, the signal that we're seeing. And this is because of these properties that we mentioned before. They are like little magnets. So, those of us here sitting in the room and maybe looking at this online, and hopefully you're not in a magnet at that time because then this won't be appropriate. But in their natural, state out, not in an MR system, all these little magnets in the protons in our body are randomly aligned. But what happens is if you put them in a really strong magnetic field, they tend to line up themselves and then become essentially give some magnetic properties to the sample or to your patient. So naturally, at equilibrium, they kind of look like this, where the little magnets that are, that are the nuclei of the proton, they're randomly aligned. So altogether, there's no magnetic field. Well, one of the consequences of using a strong magnet is when you put something like this in a very strong magnet, they start to line up with the magnetic field. And because of the properties, some of are parallel or go, line up with the field, and some actually line up in the opposite direction or anti-parallel. And the difference is in these two populations are small, but there is enough of a difference where now your sample has some of magnetization of its own that is parallel to the main field. And I'll jump in here and say that this is kind of one of the reasons why we like stronger magnets and why, we have been gradually using magnets with stronger and stronger main fields. We started off with 1.5, 25, 30 years ago. We're at 3T for a long while. Now we're in the midst of, taking off with 7T. But it essentially makes the resultant magnetic field from the sample that much stronger, which means you have more signal to work with. So now that we have our magnets and our sample is magnetized and we're ready to give a signal, then we get to talk about resonance. So when these species are sitting there in the magnetic field, like all atoms and small subatomic species, they're not just sitting still and at rest like we hope they would be. They're actually vibrating, moving around. But the action that is of interest to us is called precession. And this is where those small magnetic moments in each of the atoms, in each of the nuclei, are rotating around the main magnetic field. So here you can see there is our field on the right bottom corner that represents the main strong field of our MRI magnet. And then the nuclei are kind of spinning like a top almost around this main magnetic field. And there's a video here that kind of illustrates how this works. Now, there are a couple things going on here, but what we're interested in is the rotation of the yellow arrow around the z-axis. You can see it's also moving along that axis, but the primary action we want to look here at is this rotation around the z-axis that we call precession. All right. And as we have this this diagram up here, just want to take this opportunity to just establish a basic coordinate system. So for the little bit of math that we're going to talk about, Z in MR parlance typically means the main axis of the magnet. So here it's shown vertically for convenience for showing the rotation. In practical purposes, this is horizontal because the tube of our magnet is horizontal. So then the field lines that represent that main strong magnetic field run horizontally. And then X and Y is that plane perpendicular to that main field. Is that reasonable? Any questions or concerns about? So now we have our protons, the little magnets that make up, that they're generating, spinning around this main field. And the frequency at which they do this is determined by that B0, which is the strength of the main field. And then this other variable here called gamma, and this is actually fixed per nuclei or per species that you're imaging. So what this tells you is per unit of magnetic field, how much frequency you can get out of that. So for example, for proton, this gamma is about 42.5 megahertz per Tesla. So which means if you're imaging at a 1.5, then your resonance frequency, this omega 0 for the system, is about 63 megahertz. At 3T, we were, depending on where our systems were tuned, between 125 and 127 megahertz. And for where we like to be right now, at 7T, this omega 0 for proton ends up being about 300 megahertz. So this is the frequency now at which these species are rotating, are vibrating, are precessing in our systems. Now, in this state, where they're aligned and precessing parallel to that main field, we actually cannot see these or detect these. So where that resultant magnetization of your sample, your patient, remains aligned with the main field, we can't detect that as it is laying there. So what we have to do is we have to move some of that magnetization, that of the sample into that XY plane, essentially perpendicular to the main field alignment. And we rely on resonance to be able to accomplish this. Now, resonance means essentially matching that frequency of vibration of the protons, or precession in this case. And the other real-world example of resonance is essentially pushing somebody on a swing. So, we know that as you're swinging, if you're pushing someone, as they come back to you and as they just start moving away, you give them a little push, they go that much further every time. And it doesn't take much energy, but that just keeps adding up over time. So, you just push them a little bit at the right time, and you do that every time they come back, they can get pretty high on the swing, pretty quickly. If you don't match that and say you push while they're coming back to you, then you're kind of canceling their momentum and their energy. And the net result is they don't go as far, or they may even stop. So matching that frequency at which energy is put into their swing essentially allows them to go further. And in the case of these vibrating nuclei about the magnetic field, it allows you to move them efficiently out of that parallel alignment into this perpendicular plane. So now this video does actually show this. So this sine wave here, oscillating in the XY plane now, is applying energy, and it's rotating that yellow vector, the magnetization, down into the XY plane. And this is now where we can detect it. And this is what we use our RF coils for. We use them both to inject this RF energy into the system so that we can detect it, but we also use it now, after that injection phase is done, to detect the signal coming back out as these protons want to get back into equilibrium. Any questions or any thoughts? Okay. So just to recap, if you want to detect any signal, you have to get that magnetization out of parallel alignment into some or all of it into that perpendicular XY plane, so you can detect it with our RF hardware. We want to be on resonance to be able to move your protons or move your magnetization that way. And if you're off resonance, you're essentially wasting energy putting it into the system, but it's not doing anything with the protons. And this can actually lead to heating. And this is, in MR terms, we call this SAR. So even if you're doing everything perfectly, you end up losing a little bit of energy as heat in your subject or sample, but you really want to minimize this. The last thing I'll say here is that, we have this uniform B0. Sorry, get this out of the way. And if B0 is uniform everywhere, then all your nuclei or your protons are precessing with the same frequency. So it's hard to get location information out of that. So then what we need to do is to essentially figure out, okay, now that we have our magnets and we can get our protons resonating so we can get a signal, how do we do imaging from that? So this is kind of representing that case where we have our magnets, which are usually these long cylindrical tubes. The field that a magnet is defined to have is usually in a ball of some defined diameter at the center of that magnet. So even if we have a 7T system, it's only 7T in about a 40 to 50 centimeter ball right at the center of the system. And this is generally the case for all MR scanners. Same for a 3T, there's a 40 to 50 to 60 centimeter ball at the center of the scanner where only in that region it's 3T, and everywhere else it's kind of falls off. But within that ball, it's pretty uniform. So if you have one sample in there, one species, everything's uniform, then everything is going to precess at that same signal. So if we wanted to get location information out of that, what Lauterbur figured out was you apply essentially a controlled distortion to that field, that main field. And in most in cases, it's a linear distortion or something close to linear. So that at the center here, you can see the field is unchanged, but on one side, where the gradient adds to the field, you'll have an increased field here, and on the other side, where the gradient is on the opposite, has the opposite polarity, then you take away from the field. So the field is slightly lower here. And in this case, now you can essentially vary the frequency that protons here are precessing at versus what they're precessing at here. So again, if we go back to our basic equation that whatever our resonant frequency is depends on the field that we're seeing, for imaging, we make that spatially variant so that now the frequency that you're precessing at actually is a function of your position. And we like to formulate it in this way because here it's clear that you have this main field, and then you have this gradient that's attached onto it that's giving you this spatial variation. And this is usually in the form, on the order of Tesla, which is about 10,000 Gauss. Gradients are usually on the order of tens to hundreds of Gauss. So essentially, 0.1 to 1% of this main field. But that's usually enough now to start giving us the ability to localize protons to a given position. The first case I'm showing here is using this variation in position to excite protons in a given location at any given time. So for example, if we wanted to excite protons in this slab here denoted omega 1, when you put your subject in the magnet, you have to landmark them. So essentially, the magnet knows where every position on the subject is to a pretty high degree of accuracy. So if you want to image at this point here, then the magnet knows, okay, if I apply a gradient of this magnitude, then my resonant frequency is going to be, whatever B0 plus GZ is for this position here. It's going to transmit RF at that frequency, and then it will only excite, essentially tip your magnetization in this location. And then it does that for these different locations. And we can kind of expand this more generally into multiple dimensions. So we call it frequency encoding, phase encoding, and the underlying math and physics, they all are kind of the same thing, and we just give them different labels for convenience for referring. So in this first case here, we're doing slice selection, and this is a form of 2D encoding. But if we expand this kind of encoding with using our gradients into 1, 2, you can do it in even 3 dimensions. That's it's a bit more complex, but the math essentially is almost equivalent, or it's equivalent between the 3 dimensions for encoding. So let's look at this a slightly different way visually here. So previously we were showing, okay, you can vary your frequency over position and then just excite the protons in that slab of tissue. So that's part of the process we call slice excitation. What we can do now is within that slice, if we turn on a gradient now across, so previously we were showing from a gradient along the subject's head to foot, and that's along the Z, if we're thinking of the magnet field aligning up horizontally in the Z-axis. And now across the subject's, right side to left side, that's usually along the X-axis. And here now, you can see where the where the gradient has a slightly opposite polarity, or has the opposite polarity to the main field. It is subtracting or making the field slightly lower here. So then this is lowering the frequency of the protons precessing on this side of the subject. On the other side, where now the polarity field is adding or is in the same direction as the main field, the protons on this side of the subject are processing faster. So now you have this other dimension now of frequency variation. When you have these different frequencies adding up, you get a waveform that looks something like this. And if you actually look at the raw MR signal you're getting in an RF coil, it's not going to look too different from this. You're going to see these oscillations back and forth. But it turns out there's a very convenient branch of math that's built for taking waveforms like this that are known to have these specific frequency components and breaking them back down so that we can get the amplitude of each component. And this is basically the math that we're doing with MR excitation and detection. This is essentially Fourier analysis. So what we're doing is we're exciting our signals, we're turning on our gradients, we're creating this frequency distribution, and then we're using Fourier analysis to essentially take the signal that we're getting and getting back that distribution of protons that's giving us this frequency variation. So this is what I was hinting at earlier, trying to get to earlier when saying that the Fourier analysis with this type of encoding with your gradients, where you essentially vary the field positionally and what it does to the protons and the signal that you're getting from them, can be unwrapped in all dimensions equally with Fourier analysis. So any questions? I know that's quite a bit to unpack or think about. So in essence, we're using our gradients to change how the protons behave spatially and how they transmit RF. And the RF we're detecting, we're using that known variation in the gradient, in spatial distribution of the gradients, and using that to essentially un-Fourier or do the Fourier inverse on our signal and get back an image. So one additional concept tied to this is how this is encoded. So this is a kind of a schematic of what the gradients in an MR system are doing for a very basic type of imaging sequence. So this is probably one of the more basic imaging sequences. There are a few simpler ones, but if you want to get a simple two-dimensional image, this is about as basic as you can get. So you transmit your RF, and we had one gradient on here that would select which slab of tissue we're going to excite. So that's this GZ here. And now we want to encode some spatial information into the slab of tissue that we've excited. So that's what we're doing here with these gradients along GX and GY. And then to read out the information, we're going to then turn off these two gradients here in GX and GY and just turn back this one here in GX. So even though we call these encoding gradients and this typically a readout gradient, because this is where we're actually doing signal detection, the net effect of the gradients on our signal and the properties of the signal actually can be accounted for by taking the total area over time of each gradient. So this is kind of called the time integral, essentially adding up the effects of the gradient areas over time. So this is what we call essentially doing K-space encoding, where Gx, and you track what's happening to the area here that, this, when you take the time integral of the Gy waveform, this will determine where you are over time going along this Ky axis. So if you take the integral of Gy over time, right? So you turn it on at this point here. So then you start marching along the Y direction. But at the same time, you turn the gradient on in X. You also start marching along this X direction here negatively. So you're going negative Kx. So you end up in this corner of this encoding space. And then when you turn these off here, and then you turn back on X in the positive direction, that's going to march you back in the positive X direction. So where you are with your gradients, and in this space called K space, so this represents a time integral of the gradients, this determines encoding the information that you need to reconstruct your image. Now, each of these points here kind of represents, one of those frequencies that you're, these spatial frequencies that we're encoding. And the Hutel functional MR book has a nice graphical representation of that. So in 1D, the examples that we had where we just looked at, okay, one frequency in one position, frequency in another position, frequency in another position. You add these up, we get this waveform here with a lot of variation over time, but you can extend that to multiple dimensions. So for example, this pattern of variation here is encoded by this B1 position in K space. So if you were to take if you had some energy here, and what that did, what that would represent in the image, if you just had that point alone, that's what you would get. Along along KY, whereas just B2, so now we're varying in Y, and this is at a slightly lower frequency than B1 because you're not as far out. So this is a slightly lower pattern of spatial variation, but now in the Y direction. And then if you had something that's, say, 1 unit out in X and 1 in Y, then you're varying along both axes simultaneously, but along now this diagonal. And when you add these together, you get something that looks like this. But the Fourier analysis allows you to go back and forth between these two domains losslessly. Like these are equivalent representations of information. And this frightening looking equation here, which is the last one I think I have in the lecture, this is just saying that this MXY, this represents the image that we're trying to get at. This is the image we want to get at the end. This S here is our signal that we're trying to detect. And this is saying here that this magnetization coupled with where we are in K space and the effects over position, this gives you back the signal that we're detecting over time. And this is just, believe it or not, a simple Fourier transform relationship. So when we essentially take the inverse Fourier transform of this, this relationship, we can use our signal, put back in the spatial variations we know we're encoding, and recover the image that we want to get, this MXY. So I have a couple of papers here that these are, kind of good to, these will be nice references if you want to get a bit more into the math behind this. Let's say if we were to take, President Lincoln's portrait and take the Fourier transform of it, it would look something like this. There's a bright spot in the middle and around the middle representing the bulk of the brightness energy in that portrait, in the image. And then this speckling out further out represents, more of the edge information, the detail in the image. So if you take, that Fourier transform and you try to go backwards, but just using components of it, you can see that if you just take the outer edges and take away and, not use the middle information, you get a lot of the edge information and details. And if you do the inverse, you get, this most of the energy and a lot of the features, but you're missing a lot of the detail that you would need to, that you would normally get from these outer points. And, over time, I showed the schematic I showed previously of acquiring, doing your excitation and then traversing through K-space to get one line. That's how MR started off, just getting one line of data at a time. Pretty quickly, though, people wanted to try to figure out more efficient schemes of getting data more quickly. This here represents, a general way of doing echoplanar imaging, where we would do our same excitation of, our slab of tissue in the beginning, but now we would turn our gradients on and off as quickly as we can and just zip through all of what we call our encoding space, our K space, so that we would get all of the, all of that frequency information that we need to reconstruct our image. That's not the only way. Spiral was in vogue for quite a while, and is still used for some applications where, its properties might be more appropriate. But what I want you to appreciate here is just a couple of things that, about how this encoding space works. So one thing to notice is how the math falls out. In one domain, in K-space, this difference between your sampling points is actually inversely proportional to your field of view in your image space that you want to get. Which means that if you have, smaller step sizes here, if you're getting more points in K-space, more detailed points, you have a larger field of view here. Whereas, if you're jumping around in K-space, you have, larger gaps, then you have a smaller field of view that you're acquiring. The next point is how far out you go in K-space. So remember from that example of President Lincoln, if we don't go very far out, if we just get information right around the middle, very blurry. And that affects essentially your experiment's resolution. So if you want to get higher resolution data, you need to acquire more K-space. You need to go further out in your K-space extent. And that means, from a practical point of view, when you're running your experiment, you either need to drive your gradients harder or faster or both. So you can kind of start to get some idea now why doing these high resolution, high speed we call echoplanar imaging techniques or high speeds techniques using spiral, why they're so demanding on the system. It's been a while now where the manufacturers have figured out how they can do this efficiently. So now these days, the practical limits are not what the hardware can do, but what the FDA sets on what we can expose our subjects to. So all clinical systems right now for full body gradients are limited to slew rates of 200 millitesla per meter per millisecond. I will say, having been in systems where we get to that, you definitely do feel it. I don't know of any cases where it actually hurts you, but it does affect subject comfort. So one way that we and the vendors are now offering more options is to use what's called local head gradients or local gradient coils, where you're not exposing the entire subjects, or you're not exposing as large a field of view to these larger gradients and switching faster. You're doing the gradient switching over a much smaller field of view, and this allows us to push the performance and do some more fancy things with our imaging. One other thing I want to consider, bring up here, and this is really for our experimental consideration, because I get asked this question every time we help people set up their experiments, is with acceleration and how much data you can essentially skip. So remember, from our basic echoplanar imaging, you have to, if you want to collect all the data for an image, you essentially go through and collect every single line of k-space that you need to make up that image. However, you have full control over what your scanner does, your experiments. And you can actually collect less data than you would need to collect for a full resolution experiment. So remember, if we just collect same steps here in k-space, but we don't go as far out. So we're not collecting the outer bounds of k-space, then we're essentially losing resolution, because these higher k-space values out to the edges, these are what give us our fine edges, so our resolution. So that's one option. But what actually people do now in various flavors of it is what's called, where instead of not collecting the edges, is they do collect the full extent of k-space, but they skip intermediate lines. Now remember, with our relationship between image space and k-space, if now you increase the steps in your k-space, then you're reducing your field of view. So that's what's shown here. Because now we've essentially doubled the spacing in y, in k-space, we essentially halved our field of view in our image space along y. And this gives rise to image aliasing. So this is why, if you don't do anything and you collect data like this, you're going to have your images folded over on each other like this. And here's another kind of more schematic representation of that, where if you collect, this every other line of data, now you're essentially reducing your field of view by half in this dimension. But if you can figure out ways to fill in that information, you can reconstruct your image fully without aliasing, without those artifacts. And there are multiple algorithms and techniques that have been developed over time. I was wondering if that DOI for the Prusman Sense paper was real, but it actually is. So it's a bit of a bear to track down, but it is the actual DOI for that paper. But these here represent different techniques that have been developed over time to acquire less data through your acquisition phase, and then use some additional information that you don't take as much time or resources to acquire to kind of fill in those missing bits of k-space, so you essentially have a full high-resolution image. Right. I think that's for the imaging section. Is there any questions or any comments?
I have a question about the gradients that you mentioned. You said that and the hardware can achieve very strong gradients, and that you can feel it, but it's uncomfortable but not dangerous. Maybe you can elaborate on that. What do you feel? Or if my person in the scanner now says, oh, I'm feeling something, is that an adverse event? Is that normal? Do I need to immediately contact the emergency line? What do I do?
So the question was in terms of if you're imaging in such a way with your gradients that you're pushing the limits, but your participants are feeling something, how do you handle that? How do you respond? So as I've said, in my case, in the cases that I've done and I've experienced it, it's no long-term effects. It is uncomfortable. So you do leave it to your participants whether they want to continue or not. Most protocols have language written in that should warn the subjects that they may feel these sensations. So, and there are cases where an imaging protocol that will work on most people, maybe somebody else, because they have some differences in their anatomy, their nerve or muscle fibers. Maybe they're more susceptible to having these long conductive paths where these switching gradients can induce currents that they may feel. So in this case, you should always leave it up to your subject if they want to continue or not, if they're comfortable. And because it is always at their discretion if they want to continue or not.
I think it's worth pointing out that the fields we mean, the effects of the gradient, the stimulation gradients being switched, is insufficient to, I mean, it's enough to trigger nerves to see something, but it's not sufficient to, for example, cause cardiac arrest. So the important thing is that basically as soon as the scan stops, the sensation gets away. It can be a comfortable lights, but if you turn it on, there's no harm there. So it's not going to stop someone's heart.
Yeah.
That's good to know.
Yeah. So comment from the So there's a comment in the room that the currents induced by gradient switching are at least an order of magnitude less than what it would be to induce any kind of cardiac event or any other kind of neural event. So, or any other
online question. Can you talk more about how phase encoding works?
So online question is talking about how phase encoding works. If they want to, I can follow up on that. That's a little bit more involved. I'd say the math is essentially spreads out in all dimensions, the Fourier encoding. So even though we may talk about frequency and phase, once you let the math do its thing, it's equivalent in all three dimensions with the gradient encoding. But the person can feel free to reach out to me directly after and try to point some more information. All right. Thanks for the questions. That was good. So let's talk a little bit now about how all of this gives us contrast and lets us see what we want to see. So back to our frame of reference, we have X, Y, and Z. I do have to apologize. This is not a right-handed coordinate system. I should have swapped the X and Y planes here. So my next version, I'll correct that. This is the pedantic in me. But now we have our B0 field aligned along the Z-axis. So this is commonly, common arrangement. And when you just put our subject and our sampling, we have the magnetization with their protons lining up with the main field. So this is kind of our equilibrium state. When we just put them in, nothing is running in the scanner. Keep in mind, whatever we do, the protons, the species in your sample are trying to get back to this state where things are aligned along Z and there's nothing in the XY plane. To image, we apply our gradients, we apply our RF, and we tip that magnetization down into XY where we can detect it. Now, for the first bit of contrast, it's essentially getting back to recovering that longitudinal magnetization along the Z-axis. So when you tip the magnetization away into XY, then it wants to start regrowing back. And after you do your imaging, at your next imaging event, you're going to tip this magnetization back into your XY plane, whatever has recovered. So this here is this relaxation process is what we call longitudinal or T1 relaxation, because you're recovering back to its equilibrium state. Thing to note here is the longer your T1 of your species, the lower signal you're going to get. So think about it. If you have a longer T1, it means this is going to regrow much more slowly. So the next time you excite, there's going to be a smaller vector to tip down for you to detect. So this is another thing to think about when going to stronger fields. At lower field systems like 0.5, 1.5, T1 is actually shorter than it is at, say, 3T or 7T. So as you go to higher fields, T1 actually lengthens. So this is kind of capturing what I was just saying. And the image type that we acquire most frequently here for the researchers is our anatomical MP RAGE images, which is T1 weighted, mostly T1 weighted. And in this case here, you can see our gray matter happens to be gray in this image. And all the axons, the connecting tissue here is what we call white matter. It's a little bit lighter. So in this case, it means that this gray matter here has a longer T1 than our white matter tissue does. The next bit of the relaxation process or back to equilibrium process that we leverage is T2. So now we have our magnetization in the XY plane. But remember, equilibrium is no magnetization in that plane at all. So this is going to decay away over time. With the T2 process, that means the spins are kind of interacting with each other. So think of little magnets all kind of rotating next to each other and interacting with each other. And that will essentially naturally bring them out of alignment over time and decay away that signal. So in this case, as this is in this plane and it's rotating, like the movies you showed earlier, because these are made up of billions and trillions of tiny species, as they all essentially lose coherence with each other, then this vector is going to get shorter and shorter and decay away. But in this case now, the T2 determines how long it takes to decay away. So a longer T2 here actually means higher signal. And then so then that means this is what a more heavily T2 weighted image looks like. So in this case, the CSF is nice and bright because that's mostly water. So the T2 relaxation there is pretty long. Gray matter here has a slightly longer T2 than the white matter. It's a little bit brighter. And then the part that we're most interested in for bold imaging is actually related to T2, but instead of with just the species interacting with each other and causing each other to dephase, there's the background gradient between blood vessels and tissue that is coming into play here. And this is what we call T2 star, where it's like this dephasing of the spins, but not because of their interactions with each other, but because with the background gradients. If we're looking at what happens in brain tissue, and this is essentially the cylinder here represents the cross-section of a blood vessel, and the surrounding is brain tissue. This schematic here represents what we'd like to think of as a non-active brain state, where maybe not doing anything, and there is kind of an equilibrium level of deoxyhemoglobin in the blood vessel, and then the outside of the blood vessel, mostly water, electrolytes, what you think of as extracellular fluid. Deoxyhemoglobin is making the magnetic field inside that blood vessel a little bit stronger. And that's why in this diagram here, the field lines are closer together. That means a slightly stronger magnetic field. And what Peter had mentioned in his first lecture is that when that region of brain tissue becomes active, it drives up essentially the metabolic demand because now that brain tissue is actually working, but now the metabolic supply of oxygen, oxyhemoglobin, and nutrients actually overcompensates for that increase in usage, increase in demand. So then the amount of deoxyhemoglobin in the blood vessel drops. So you have more oxyhemoglobin in the blood vessel, and that actually makes the field here more uniform with the external tissue. In this case here, if you're imaging, it means that if you're looking at the gradients between outside and inside, this is fractions of a millimeter, this is going to be a more uniform situation. So your signal is going to decay away more slowly than it would in this case. So here you have a bigger gradient between your tissue and your blood vessel. So this stronger gradient here will cause your signal to decay away more quickly. And when we look at the time series of a functional MRI experiment, if we to look at the signal that was happening in this voxel over time, these lower signal values here would represent those cases where there's more deoxyhemoglobin. The field is less uniform, so it dephases more quickly, so the signal is lower. And then when the brain is working, doing task, there's more oxygen, more oxyhemoglobin supplied, field is more uniform, so the signal remains higher. And then we do that over space and we do our statistics properly, and you start to get maps that look like this for brain function. Any questions or any thoughts or? Okay. Yes.
You mentioned the changes that were occurring in brain tissue, but in the diagram, the magnetic field was changing intravascularly as well.
Yes, yes. Yeah. Oh, so comment was mentioned, I said about the field changing in the brain tissue, whereas the diagram showed intravascular effects of the field. So the effect is the gradient, because a magnetic field is not, it's not just a pinpoint, it extends over space. So even though the field changes is happening mainly inside what's happening inside the blood vessel, that does create a gradient between the field in the blood vessel and then what's happening extravascularly. So there's that gradient in the magnetic field across space, not just confined to within the blood vessel. Did I get that? All right, thank you. All right, so these are just a few of the common basic types of contrast that we are looking at most frequently for the types of experiments that that we support and that most of our researchers are interested in. But it is by no means the end of what is what is possible with MR. In case this hasn't been apparent, it is very sensitive to timing and what you do with your gradients and how you play your RF and the relative timing of those to each other. So you can sensitize those magnetic moments in your water molecules to entirely different environments and effects. So this is just a sampling of some of the major imaging techniques that have developed over the years, but it is by no means exhaustive. All right, and then let's just wind this up with a few things for you to consider as you're thinking about your experiments. So as we started off, stronger magnets give you more signal to work with. So if you're interested in doing something very high resolution, then you want to think about stronger magnetic fields. So using one of our higher field systems. Also, we talked about the relaxation properties changing depending on what field you use. So then you can also exploit that, with different fields and seeing what's more optimized for what you're looking at. However, if you're using stronger magnets, that might not be suitable for all applications. If you have a patient population where there are common implanted devices, we don't have as broad device clearance for 7T yet as we do for 3T. And as these fields get higher, there are more SAR issues. And also with just keeping the fields uniform or as controlled as you need them to be for good imaging to happen. We also want to think, is it important for you to think about relaxation times? And if you're looking at particular species, maybe if you're doing spectroscopy experiments, or, you have to look at certain metabolites, specific metabolites, maybe you're more sensitive, things like that. I think one of the biggest questions people have to answer, I always get the question, I want the whole brain and I want it in half a second. But as you can see, when we're talking about with acceleration and resolution and how much time it takes and how hard you can drive your gradients, these are all things that you have to consider with how much signal you're going to get at the end, how much noise. So when you accelerate, you're collecting less data, and that makes you more susceptible to noise. So if you have a very weak effect, that might not be the best choice for you, because then your effect might get swamped in the noise that you're generating by collecting less data. So, these are all things to think about and consider and discuss with us as a physicist, discuss with the statisticians, and, with folks that are, that can help with designing your experiment. The last thing I'll say here is, with everything that all the data that we're collecting, there's always more that you can measure, more data that you can collect. Does your experiment depend on your subject staying alert? Should you collect eye tracking data? Should you collect EEG with this? We have a group now that's working with a field camera. So this is collecting all the magnetic field changes that are happening in the scanner during our experiment, including things like respiration effects. Is that something that's useful to you, that you can use? So just keep in mind, there is a cost to adding, to collecting more and more. It's complexity, it's making sure things work all the time, setup. So a lot of times, it's good to figure out upfront, what is good for me to collect to do this robustly, repeatedly. And then finally, I'll just give this one last overview of, how systems are typically set up. If you haven't seen this, hopefully you have by now. But, there is an MR. So this is the MR magnet, and this is, a bed where patient or sample would go onto and go into here for imaging. In our facility and most of the others around here, we usually have some sort of MR safe stimulus hardware that's part of the suite in the magnet room itself to help deliver stimuli, get responses from your subject. All of this is supported and driven by essentially a mini data center's room worth of electronics and power. So there's a lot of hardware at the back here to make those gradients work as hard as we need them to work, to get the the resolution and the time, the spatial and the temporal resolution that we want, and do that reliably and cleanly. We interact with all of this from control room, where we can we can talk to our subjects, we can run our experiments, and then finally all of this data gets sent. Here it's going directly off to your lab's machines. We have some relay machines in the middle that we tend to aggregate our data on to make it a little bit easier for folks to collect and that data from. So, all right, that's all I had. Are there any final questions? I'll happy to take those.
Maybe one question.
Sure.
You talked about where the signal comes from, where the contrast comes from, where does the noise come from?
So the question was, we've talked about signal and we've talked about contrast and where, where those come from here. And the question was, where does the noise come from? And I like to think noise of here as, maybe something we didn't account for, or maybe it's getting in the way of what we want to detect. So there are two primary sources of noise in the traditional sense, but maybe not in the modern sense, that we try to factor in. So one is noise in the system and essentially in the technology. We can only drive our amplifiers so fast. We can only put that much power through our RF hardware. We can only detect that, that small of a signal before thermal noise starts introducing its own fluctuations into that. So if you're imaging a very small, tiny voxel, there are fewer protons and species in there to generate magnetization for you to detect. And then you start becoming susceptible to things like thermal fluctuations and randomness at the very low level. So this is, I think, maybe thermal noise is not the best term for that. It's kind of a catch-all, but system noise, basic limits of the hardware. I think the other part of that noise where it's a lot harder to deal with, because the hardware has gotten really good now. So that's actually not the majority of the problem that we have to consider now. The majority is actually in the subjects ourselves that we have to contend with. So things like breathing, heartbeats, when we're in the scanner or when subjects are in the scanner, or chest moves, there's pulsations of blood vessels. So all these little fluctuations / perturbations, maybe they're twitching or they're moving as they're in there. These they're not, in the traditional sense of the word, these are not noise because they still get encoded into the signal and we detect them, but they're varying our signal, or they're modulating our signal in ways that we're not controlling and usually not accounting for unless we collect some of this additional information that I mentioned at the end that we can maybe try to correct for those effects for. So does that maybe get it? Yeah. So anything else from online?
I think I answered the common question about where to get the video.
Okay. All right. And if that's it, then thank you.